Today's topic is adjusting the domain to solve more complex trigonometric equations.
All right, so how do we use our calculator to solve any of these problems, to double check? In these basic cases, you should be getting them in the non-calculator section, but there are times you might get one in the calculator section as part of a bigger problem. So being able to do it quickly is fairly important. I'm going to do question 1b, which asks me to solve cos x. And to do that, first of all, we simply just can go into algebra and we are going to solve an equation. So that brings up the solve. To type in cos, I can either type in COS on my calculator, or I can go through the trig menu here. Hopefully you can see that. Trig cos is what we're looking for. That'll bring that up. They're the two ways to get cos in there. So cos of x is equal to, and in this case, we're looking for the square root of, where's the square root button on the calculator? Oh, it doesn't matter. I have a shortcut because I can also, maybe it's not a shortcut, but I can do square root like that. Equals the square root of 3 divided by 2. So that's what we're trying to solve. I'm going to put in a comma x to say that's what we're solving for. And then I need to give the domain. I want to solve it for 0 to 4 pi. And there's a really important button that you need to do this after the bracket. So we need to be after the bracket. We press Control equals, brings up to this dialog box, which has got our greater than, less than, greater than or equal to symbols. And this one here, this straight bar, is used to define a domain. So I'm going to just put that straight bar after the brackets. This is a really important step. I'm going to show you the consequences of not doing it in a minute. But now I'm going to say we are going from and we need to write it using the notation that says 0 is less than or equal to x, which is less than or equal to 2 pi. Press enter. There are my solutions. So it's a really easy way to get our two solutions. If you want approximate solutions, remember you can just press Control Enter. If you're doing any sort of numerical problem, an applications problem, you don't want approximate solutions like that. So you can just type the equation in and make sure you give it a domain. Let's see what happens if I don't give it a domain. I guarantee you a really common error. People are learning this and they don't do it properly in a test or an exam situation. You forget what you need to do. Let me solve a different one that says, oh no, I'll do the same thing. Square root 3 divided by 2, comma x. And we get this thing. It doesn't spit out an error. It doesn't say there's a problem here, you need the domain. What it does instead is give you this weird answer that's got this n3 variable and n3 here. Now, what this is actually doing is giving you something related to the general formula of a trigonometric equation. There's a very important concept called the general formula. I'm going to I'm going to stop projecting my laptop screen now and start projecting my iPad again because I've got something on my iPad I want to show you. All right, so the takeaway message from here is if you do get something like that, the easiest thing to remember is, oh, I didn't put my domain in. I'll just go back and put my domain in. But it's also reasonably important that you understand what's going on and why it gives you those answers. Now, here is, hopefully you're seeing the formula sheet. I've got up on my iPad, I've got the formula sheet at the moment. And page 2 is our trig stuff. At the top here, we've got our how to convert from degrees to radians and radians to degrees. And then we've got our then we've got some basic identities. We have already talked about the first and the second, and the third and the fourth and the fifth ones don't really matter. We'll talk about them a bit later. We've also talked about our table of exact values. We mentioned our cast diagram, but I've said you're not going to use it really. These things here, these are related to the trig graphs that we looked at on Tuesday, but I've also said they're not that important at the moment, so we are going to come back and look at them. When we do trig graphs, all this stuff is going to be important, but I'm going to skip over that for now because that's all related to graphs. And then right at the bottom, you've also got this trigonometric equations, which just sounds like it's related to what we're doing at the moment. We are solving trigonometric equations, and here you are given the general formula for trigonometric equations. And so that output that the calculator gave is actually what you would get if you plugged numbers in here. So in that particular case, we were trying to solve a cos x equation, and x is equal to 2 times n times pi, where n is an integer. So n is 1 or 2 or 3 or 4 or 5, plus or minus r cos a, which is essentially saying what you get when you look up your base angle of a. So it gives us the numerical formula for solving it, and the calculator is using that. And there are some people, and indeed some people who teach this course and some students who use this course, who learn that method of solving these equations. I want to stress, and that's why it's on the formula sheet, I want to stress to you that we at the Friend School don't really think that method works. It's way too complex. It doesn't teach any understanding. And we much prefer the method that I have shown you in that video. So we much prefer you to have a better understanding of, okay, well, if I'm solving cos of x is equal to root 3 on 2, then we know, okay, well, cos is going to be positive. That means we're in that quadrant and we're in that quadrant. And my base angle is going to be equal to pi on, what's that? Cos of, that's going to be pi on 6. So my base angle is going to be pi on 6, which means I'm going to get a solution there at pi on 6. And I'm going to get a solution there at, well, this is really 2 pi. I'm doing this very quickly and with poor communication, but we're going to get an answer of x is equal to pi on 6, and x is equal to 2 pi minus pi on 6, which is 11 pi on 6. So that is what I think is a much faster and easier way, and also shows understanding of what's going on, as opposed to just plugging numbers into a formula that you don't understand, that is way too complex and spits out numbers that you then have to interpret in weird ways. So the takeaway lesson from here, as I've said under my live video, there's a few things I want to talk about. First one is showing you how to do these questions on a calculator. I've done that. The second is, what is the general equation? Well, I've shown you that, but as I've also said here, I'm not expecting anyone to use it. I don't want people to use it. You're allowed to if it makes sense. You're allowed to if you find it easier. But I've not met anyone who, after showing both methods to them, actually prefer, and after they genuinely understand both methods, I've not met anyone who prefers the formula to just that method of manipulation. I'm about to go on and show you a more complex example of solving all of these equations, but before I do, I might just pause and ask if anyone has any questions about anything that happened in the video or that I've talked about this morning. Let's talk about a more advanced example. What we're going to see here, so far everything that I've looked at, as I mentioned, if you got to the video, the end of the video said we're going to see what happens in the more complex example. Everything we've looked at so far is a single value of x inside the brackets, or theta, or an angle inside the brackets, and we haven't ever dealt with what it might be if there's a more complex situation. So right now, I've got this example on the screen, and for what I'm about to do, it requires a little bit of understanding of the graph. Let's just remember what the graph of cos x looks like. The graph of cos x from 0 to 2 pi, we're going to have, and I haven't talked about doing graphs because so far all the graphing that you've seen has been Desmos, and you haven't seen me do it manually, which I'm going to do a lot more of next week. All right, so the graph of cos x, we start at 1, go down. That's our sort of cos x graph. And what we're thinking of in this equation, let's think about what this equation up here is actually asking us to do. This equation up here is actually asking us whereabouts is cos x equal to root 3 on 2. Well, root 3 on 2 is reasonably close to 1. So if I draw a dotted line across here, it's essentially asking where do we cross, which is going to give us that answer. Here we've got an answer at pi on 6. And then we've got this answer. We're going to get an answer at 11 pi on 6. You'll note that pi on 6 is pi on 6 units away from that axis there, and 11 pi on 6 is pi on 6 units away from that end of the domain there. So there's a fair bit of symmetry here. My diagram isn't great. It's hard to get sign diagrams working nicely. I can do it so well on a whiteboard. The iPad's a little bit trickier. All right, let's use this knowledge to answer the question. Let's solve the equation cos of 2x equals root 3 on 2. So it's almost the same as the last question. All I've changed is what's happening on the inside. And we're going to solve this equation over the domain 0 to 2 pi. Now, let's think about what this 2x has done to my graph. We should note, and you don't have to know anything about trig graphs, you just have to know from our functions unit what graphs actually, what this is. This is going to be a dilation in the direction of the x-axis by a factor of, in the direction of the x-axis by a factor of a half. So it's going to shrink everything towards the x-axis and thus halve our period and give us double the number of periods within that length. So I'm going to draw this in green now, because green stands out a little bit better than yellow, but we should get something that looks sort of like, oops, that double dotted line wasn't my maximum. Yep, something that looks like that. So that green line there is going to be our cos 2x. Are we all happy with that? That makes sense? I know in a classroom I'd look around and hopefully see a whole bunch of people nodding, and that's a little bit harder here, but we'll make do.
So how many solutions am I going to get? Well, that's a really good question. We can see that there's a place there where our green line intersects the root 3 on 2, and a green line there, and a green line there, and a green line there. So there are 1, 2, 3, 4 places, which means we should get 4 solutions. Where are those solutions going to be? Which quadrants? Well, if we think about our usual unit circle, X and Y axes for our unit circle, I should say, and think about our quadrants, well, we've got cos is positive, and so we know that cos is positive in that quadrant and that quadrant. Now, it's really natural to assume from here that since we're going from 0 to 2 pi, we're doing that sort of circuit, and that means that we're going to get 2 solutions. It's obvious that we're getting a solution there in our quadrant 1 and a solution there in our quadrant 4. But we were expecting 4 solutions, remember? 4 up here. So where are the other 2 solutions coming from? And that's a really good question, and it's something we need to think about. What's actually happening here is that since x is going between 0 and 2 pi, then our solutions for what's 2x doing, 2x must be going between 0 and 4 pi. And so while our x is going from around this circle as I just drew, from 0 to 2 pi, our 2x, which I'll draw in blue, is going around twice. And thus we're getting a solution there, and there, and there, and there, which is corresponding to our same 4 angles up here. So we should be getting 4 solutions. Let's work it out and see what we need to do using this as our domain. Thus, when I'm solving my equation, I'm going to, let me start working on the solution just from the beginning, how I'd work it out, knowing all this, but solving the problem from the beginning. I'd write out cos 2x is equal to root 3 on 2 over the domain 0, 2 pi. That's what's given there. Thus, my first step is to work out where my solutions are. My solutions are going to be there and there for cos. My adjusted domain is going to basically say, well, since x is going between 0 and 2 pi, what's the thing inside the cos function doing? So 2x is going between, and what I need to do here is work out where the beginning and the end are by plugging x equals 0 into 2x and x equals 2 pi into 2x. Now x equals 0 times 2 gives us 0, and x equals 2 pi into 2x gives us 4 pi. In a more complex example, we might have something more complex here than just 2x. We might have half x plus pi on 4, or something else that's challenging. For now, let's just worry about 2x. I'll do an example of that one in a minute. So our adjusted domain is that, and we also still need to work out our base angle. So our base angle is going to be equal to, whereabouts is cos 3 pi on 2? Well, that occurs at pi on 6. So we're going to get solutions. So what I do now, given my unit circle solutions over here are happening there and there, I'm going to put a circle on here that goes over to my domain. So I'm going to start at 0 and go pi, 2 pi, 3 pi, 4 pi, and think about where that crosses my solutions. I'm going to label it in green. I'm going to get a solution there, and a solution there, and a solution there, and a solution there. And they are going to occur at, remember we are solving now for 2x is equal to, where are those solutions? Those solutions occur at pi on 6, and 2 pi minus pi on 6, and 2 pi plus pi on 6, and 4 pi minus pi on 6. Making all of those numbers a little bit more palatable gives us pi on 6, 11 pi on 6, 13 pi on 6, and for 24 minus 1 is 23 pi on 6. These are our answers for 2x. But of course we need to halve it because we actually want values for x. And so I'm going to halve each of these for 1, 2, 3, 4 different answers. I'm going to halve each of those simply by changing the denominator to 12. And I'm going to get pi on 12, and 11 pi on 12, and 13 pi on 12, and 23 pi on 12. And those are my answers. I can check those by typing in the question, this cos 2x equals root 3 on 2, type that into a calculator, give it the domain 0 to 2 pi, and it will spit out these 4 answers as a result.
I'm going to give you a more complex example. I know that one might seem complex enough, but I'm going to really push you here. I'm going to do an example that is like the hardest sort of a standard question, and you'll see how difficult it will get. I'm not expecting everyone to get this straight away, but I am recording the video. And I will put it up on YouTube as well later, so you can watch this back over again if you need to. This question I'm going to solve now is 2 sine 2x plus pi on 4 minus root 3 equals 0 over the domain 0 to 2 pi. How on earth are we going to solve this equation? Well, first we know our general rule is that we need to get it to a single trig ratio on one side. So I need to get rid of this. So I need to get rid of this 2 and this root 3. I'm going to add root 3 to both sides and divide by 2, and that gives me sine of 2x plus pi on 4 equals root 3 on 2. All right. Now I need to adjust my domain. I'm going to solve this. There's a few different things I need to do here. Like I can work out my base angle, or I can adjust my domain, or I can start with my diagram to work out that its sign is positive. I'm going to get solutions there and there. Any of those things sort of have to happen. It doesn't really matter what order we do them in. Let's do the ones we know how to do simply first. I can look up root 3 on 2 on my table of exact values and determine that my base angle is equal to pi on 3. I sort of already did this step where I worked out that I'm going to get solutions in that quadrant and that quadrant. Note that there's different notation. Some people prefer to draw a line like that. Other people just put a tick in both quadrants. I prefer to draw a line, especially in this question, in more difficult questions. So because it's going to need to be clear. Because of the clarity required, I'm going to draw it reasonably large so that I can show you what's going on. So that's where our angles are going to be roughly. Let's adjust our domain. And usually when you're adjusting your domain, the unadjusted domain for x is already given, but it's nice to write it out again. So x is 0 to 2 pi. Thus, the thing inside our bracket that we're adjusting for, 2x plus pi on 4, is an element of. And now what I need to do is plug 0 into my 2x plus pi on 4, which gives me pi on 4. And I also need to plug 2 pi into my 2x plus pi on 4. That's going to be 2 times 2 pi is 4 pi. 4 pi plus pi on 4 is 17 pi on 4. Or I could just write it as 4 pi plus pi on 4. It doesn't really matter which way we do it there. The next step is to think, well, way back here, remember when in this diagram I'm now talking about, remember when I just sort of went, okay, round twice, or in a black line, I went, no, now every color is getting messed up. I won't do it there. What I'm going to do now is draw circles around here, sort of like that, but it's important where I start and where I finish, because I want my start of my circle to be the beginning of the domain and the end of my circle to be the end of my domain. Now, where is pi on 4 relative to this black line that I've got here? This angle here is pi on 3, which is a third of the way around. Pi on 4 is a smaller fraction, so pi on 4 is going to be under that one. I'm going to start there. I'm going to go round. Remember that this value here is pi on 4, so now I'm at pi. Now I'm at 2 pi. I have to keep on going because I have to get to 4 pi. So now I'm at 3 pi. Now I'm at 4 pi. And then I have to go to 4 pi plus pi on 4. So I'm going to finish there. So that step is incredibly important. Basically, what we've done now is with our black lines, we've identified where my solutions are going to be. And with my red lines, I've identified how many solutions I'm going to get. So I'm now going to use green to just highlight where they intersect. I'm going to get an answer there, and an answer there, and an answer there, and an answer there. Let's work out what those are. Thus, 2x plus pi on 4 is equal to this one here. This first one is just going to be my base angle, pi on 3. My next one is going to be pi minus pi on 3. My next one is going to be 2 pi plus pi on 3. And my final one is going to be 3 pi minus pi on 3. That was that one there in green. That was that one there. And then if I keep going around the circle, I don't cross any more black lines before I get to that. This is pretty complex. This is one of the hardest things you're going to do in this unit. And there's a lot of stuff going on. But we've got a little while to practice it and get it right. I know we don't have a little while today, but I'm going to give you more time next time to practice this as well. Let's also remember as well, of course, after you get an answer, you've got your calculator, you can check every step on the way. We're not quite nearly finished. Let's keep on going. First of all, let's simplify each of these to be a nice wholesome number. So I'm going to get pi on 3, 2 pi on 3. Here we've got 2 pi plus pi on 3. 2 pi is 6 pi on 3, so plus 1 is 7 pi on 3. You're going to do a lot of this sort of fraction addition. 9 pi on 3 minus 1 gives me 8 pi on 3. That looks like 4 nice solutions. That's great, but those are actually solutions for 2x plus pi on 4. And we still need to get down to solutions for x. So how am I going to do that? Well, first of all, I'm going to need to subtract pi on 4 from each. So I'm going to need to do this step multiple times. That's going to be easier if we change all our denominators to 12. So I'm not actually going to change this left-hand side at all. This is still going to be x plus pi on 4, but just to make the next step easy, I'm going to put all of these denominators over 12, which turns this into 4 pi on 12 and 8 pi on 12 and 28 pi on 12 and 32 pi on 12. Now my next step is to subtract that pi on 4, and subtracting pi on 4 is the same as subtracting 3 pi on 12. So now I'm going to go through each of these and simply just subtract 3 from each of my numerators. That gives me pi on 12, 5 pi on 12, 25 pi on 12, 29 pi on 12, and that's my answers for x. For 2x, I want answers for x. And so to do that, I halve both sides, which means I'm going to double each denominator. And thus I get pi on 24, 5 pi on 24, 25 pi on 24, and 29 pi on 24. Those are 4 answers. They should be correct. A really good way to double check is to make sure that they're all within the original domain that we were given, which was 0 to 2 pi. So let's just see, they are all bigger than 0? Yes, that's correct. The lowest one is bigger than 0. They are all less than 2 pi. So this one, 29 pi on 24, the 29 is bigger than the 24, which tells me that it's a little bit bigger than pi, but clearly that is less than 2 pi. So they all fit within their domain. How do we actually know if they're the right answers or not? Well, let's go to our calculator and check. So again, now I'm going to swap to my calculator control. Now I'm going to type that in. The original equation was we are trying to solve 2 sine 2x plus pi divided by 4 minus the square root of 3 equals 0 over the domain. I can type this in much faster because I'm using a keyboard. I know it'll be a bit slower for you. Over the domain, 0 is less than x, which is less than 2 times pi. And I forgot my comma x. And there's my answers: pi on 24, 5 pi on 24, 25 pi on 24, and 29 pi on 24, which is exactly what I thought I would get all the way back here when I was doing it manually. So that's an example. There's a lot of stuff going on there, but that is an example of the most difficult A standard sort of question that you might get. There's nothing this complex in the textbook yet, because the main place that the textbook practices these questions is when we're solving equations, when we're finding x-intercepts of equations. What I mean by that is the main use of this is if we are sketching the graph of, if we are sketching the graph of 2 sine 2x plus pi on 4 plus root 3, we might be sketching that graph, in which case we're going to need to know the x-intercepts, and we know the x-intercepts occur when y is equal to 0. So we're going to need to go through this process as part of a graph sketching. So you might think, yeah, solving this equation is massive and has taken a long time, but it's crazy to think the main place we use it is actually part of an even bigger process, and that even bigger process is sketching a graph. So we're not going to practice too many of these really hard ones now, but question 8, out of the exercises that you've been doing, question 8 does give you some practice of adjusting the domain. And so I suggest that right now, you've got 10 minutes left of today's lesson before you get a very well-earned lunch break. But question 8 is the best place to go to practice some of these and learn the process of adjusting the domain.